this to somehow show you the main problems here. So we will discuss this in more detail later on, but just for the people who know it. So when you evaluate second order TGV, you have to minimize over a set of vector fields. You take the first order derivative of your signal, you subtract the vector field, and then you again take a derivative of the vector field. And you can see that this is somehow a bit difficult to transfer to manifold. So for instance, okay, first you have to take the derivative. You can do this maybe using the log mapping or so, but then you have something which is in the tangent space of the manifold. Then you need to subtract something. Well, this might also be possible. You just take a tangent vector, but then you have to again differentiate the tangent vectors. So this is and those generally live on different locations on the manifold. So in vector spaces, you can just identify all tangent spaces, and this is fine. But on a manifold, the problem is that these objects would then live on different spaces. And the question would be how to compare them, how to take the derivative of these objects. And this is exactly what the talk will be about. So the talk will be how to extend total generalized variation, second order total generalized variation for manifold-valued data. And as you will see, we try to do it somehow in a bit of systematic way. So we will first try to identify main properties of second order TGV, which we know from the vector space data. And then we will try to extend it in a way such that these properties are also transferred. So let me now give you a short outline of my talk. So in the first section, I will just repeat for everybody who doesn't know it, what is TGV for vector space data. Then I will show the main idea in the univariate setting, how to extend this. This is still rather easy. And then I will consider the extension of TGV in the bivariate setting, where it gets a bit more complicated. And at last, I will show some existence and well-posedness results for TGV-based denoising at a manifold-valued setting. I will briefly discuss the algorithmic approach, and at the end, I will show some nice pictures. Okay, so TGV for vector space data. Again, let's consider first the continuous setting and start with TV. So as you know, one way of defining TV would be just to test with a set of vector fields. You constrain the with the divergence of a set of smooth vector fields, and you constrain them to be less or equal than 1 in the infinity norm. And similar to the motivation before, when you do this, you get a good regularizer. You are able to, this class of functions for which TV is finite can have jump discontinuities, and this is also numerically observed that you have reconstructions with sharp interfaces. However, you have this well-known staircasing effect. And one way to overcome this would be just to go to second order. So just instead of testing with the first order divergence, you take here the second order divergence, and you use matrix fields, but you keep the same L infinity constraint. This improves upon TV, so you see that you can get rid of the staircasing effects. However, what you would expect from the function space can also be seen in the reconstruction, namely that the class of functions for which this is finite cannot have jump discontinuities. So analytically, you can never expect to get jump discontinuities, because if the second order derivative is a measure, the first order derivative must be a function. This can easily be shown, and then you cannot have jumps. And this can be seen here, that you have somehow a small smoothing of edges. And one way to overcome this is to introduce just a seemingly minor additional modification. Namely, instead of only constraining the vector fields themselves, you also constrain the first order divergence of the vector fields, which then leads you to the definition of second order TGV. And when you look at the reconstruction, you can see that you can get a bit better. In particular, you see that now you have really sharp interfaces at the boundary. And analytically, you can show that this together with the one norm spans the same function space as TV, so you have really finite values for functions which have jump discontinuities. This is so a short story in the setting. So just to give you a more idea, so what does TGV do for one-dimensional signals? So it's 0 as TV for constant signals, but now it's also 0 for linear signals. So this is somehow what you would expect, why you would expect that you don't have the staircasing effect. If you have a jump, it's finite and it penalizes the height of the jump. And if you have a jump in the first derivative, again it's finite and it penalizes the height of the jump in the first derivative. So this would be somehow the original definition, but there is a very convenient equivalent definition of TGV, the so-called dual definition or minimal definition, where you can show that TGV is the same as you would take the minimum of all vector fields of bounded deformation. You take the radon norm out of the distribution of derivative, subtract the vector field, and then you measure the symmetrous gradient. So this is a sort of gradient only with the symmetrization of the vector field. And this also gives you more an idea of what the functional does. So you can imagine that if it's, for instance, good to use TV as regularization, you would expect that the functional just picks W to be 0, so this term vanishes and you just have TV. But if it would be in regions where it's good to use higher order, so second order regularization, you can just pick W to be du, so this term vanishes, and you have here somehow now the symmetrous gradient of the gradient, which is a second order derivative. And these properties can also be phrased on the slide. So if in some region or globally W equals 0 is a minimizer, then this is TV. If W equals the derivative is a minimizer, then this is second order TV. And you also have a characterization of the null space, namely the functional is 0, if and only if the function itself is affine. So those are somehow already some of the main properties which I would like to ask you to keep in mind for the talk. So we have this representation here of TGV. We will only consider this now for the rest of the talk. And we have these properties that you can get TV, you can get second order TV, and you know how the null space of a functional looks like. So now briefly, so now we move to the discretized setting. So all of the rest of the talk will be for the discretized setting only. We only consider finite signals. And in vector spaces, you get essentially the same. So you can use this minimal representation of TGV in order to define it in the vector space setting. So for a discrete function u, you define it in a very similar way, now only that you use finite difference operations. So the gradient would be just the forward difference in x and y direction. And the symmetrous gradient, and this will also be important later on, is a backward difference in x of the first component, a backward difference in y of the second component, and then you have this mixed term here, where you take the y derivative of the first component and take the average with the x derivative of the second component. So this is the same as you would just take the Jacobian of the vector field and symmetrize it. Okay, so you just take the two values and symmetrize them, and so you have here the mean. So this is what we need to take into account when we want to extend this. And as I said, so those are just standard forward and backward differences. And if you do it the right way, so if you take care of boundary conditions and so on, you can inherit the properties that you have in the function space setting also for discrete TGV. So you can show that, first of all, if the minimum is obtained at 0, you get a discrete TV functional. If it's obtained at the derivative, you get discrete second order TV. And you can also show that TGV is 0 if and only if the function is affine, where now affine is meant in the discretized setting, so uij must be ai plus bj plus c for some constants a, b, c. Okay, so this is just a straightforward. So this would be what would affine mean in the discretized setting, and you can really show that these three properties hold true. This is an easy exercise. Okay, so now we have fixed second order TGV in the discrete setting for vector space data, and now we will come to manifold situations. Now we want to extend this to manifolds, and we want to keep these three properties in mind using this extension. So we will first consider the univariate setting. So we just have univariate signals which depend on one, so which are signals. And before we go to an extension, just a brief excursion about some basic things on manifolds. So we will just so we have two versions how to extend TGV. I will just discuss one, the more basic version, and for this we will just need two basic tools, namely the exponential and the logarithmic map. So throughout the talk, we assume now that M is a complete Riemannian manifold. For any point in M, we denote by Tu of M the tangent space, and this is just notation. And then we have to keep the following in mind. So if we take now any vector in the tangent space at a certain location U, then it's most basic fact of manifolds that there exists a unique geodesic, so a locally distance minimizing curve, the generalization of a straight line, such that the curve crosses U, and the derivative of the curve at the point U is this vector. So if you plot this graphically, so assume that you have a point in a manifold, you have a vector which lives in the tangent space, and then you have a unique curve which crosses U such that the derivative at this point exactly corresponds to the vector. Okay, and using this fact, you can define the so-called exponential map, which maps from the tangent space at the point U to the manifold, and just assigns any vector the endpoint, so to say, of this geodesic. So for any vector, you have a unique geodesic, and you just take the geodesic at at point 1, which gives you a point in a manifold. Okay, so this is the exponential map. So it maps tangential vectors to points in a manifold. And you can also revert this. So now if you assume that we have again our point U, and we have a second point Y, which is close to U for simplicity, then we can define the logarithmic map just to be this vector which would map to Y via the exponential map. So it's just, as written here. So you take your point u, you have some point y, and then you just pick this vector in the tangential plane of u, such that if you would take the x of this vector, you would arrive at y. And if you're close enough, this is a unique vector. If not, this is set-valued, but it's still it's well defined somehow. You just have to define it as a set-valued mapping. Okay, so you can, on the one hand, you can go from tangent space to manifold, and then on the other hand, you can go back from manifold to the tangent space. So we have some kind of correspondence. This is important to notice. So we have any vector in the tangent space at the point u. So we have always to consider the tangent space at a particular point. But any vector at the tangent space corresponds somehow to a point tuple. So u, which is the base point, and y, which is the end point if you take the exponential map. And this is almost a one-to-one correspondence. So for any vector, I can basically identify any vector in the tangent plane with a point tuple of 2 points u and y via this logarithmic and exponential map. And in vector spaces, so the logarithmic map is just the u minus y, and the exponential map is just y plus u. So you just have a point, a vector, and you go along the vector, or you take the vector which connects the 2 points. Okay, so we have to keep this in mind: exponential map, logarithmic map, and correspondence of vector fields and point tuples. Okay, and now we look at TGV and see how we can use these concepts to generalize it in a sense. So we start again with the definition in vector spaces using finite differences, as I had before. So we have for the difference stencil, we have the vector field and the difference of two vector fields. So consider now just a section of our signal. So we just consider 3 points of the signal: the center point, left point, right point, and just for visualization, I connect them using a geodesic interpolation. Now the first thing to generalize would be the forward difference operation. So it would be u plus minus u0 if we are at this point. Okay, so this would be two vectors which live in the tangent space, and we have already seen the logarithm. This is nothing but the logarithmic map. So we can one way would be just to generalize this forward difference operation by using the logarithmic map. This is a one-to-one correspondence. But now, if you do this, we have now the gradient is somehow an element in the tangent space, which would mean that also these w's need to be in the tangent space, and then we have again to take differences of objects which live in different tangent spaces. So this might get a bit complicated. It actually corresponds to the second version we propose, but for simplicity, one can use the identification I had before. So before I said that we can identify any vector in the tangent space by a point tuple, and this is just what we do here. So instead of taking the log, we just identify the derivative with this point tuple. Okay, so the point tuple u dot u plus is identified with the forward difference of u at this point. So we have this would somehow correspond to point tuple. Now we look at the w's, and we can do the same thing. So in principle, the w's are vectors in the tangential plane, but using the exponential map or the logarithmic map, they correspond to points. So what we can do is we just identify the w's with a point tuple. So instead of introducing w's, which live in the tangential plane, we introduce points y, which correspond to these w's. Okay? And doing so, we can rewrite this expression now just in terms of point tuples. Okay, this is still not well defined because the question is what's the difference of point tuples, but just using this identification, we can replace the vectors by the endpoints and rewrite TGV in terms of point tuples. So this would be the x, or the forward difference. Then we subtract the w1, and here this would be a forward difference operator of this point tuples. And the nice thing of this is that this can be written down just with points in the manifold, so you don't have to go to the tangent space. However, you have to ask yourself now the question: what's an appropriate distance function for point tuples? So more generally, we would now look at some distance functions d, which measure the distance of different point tuples. And we can look at the two, it could be in principle the same distance function. So we have identified now somehow these w's with point tuples, the u with w's, so we just would need one distance function. But there is still a difference, because when we look here, these 2 point tuples, they live in the same space, on the same tangential space. Okay, both live on ui. So the base point is ui for both of them. So an obvious definition of this distance would just be to take the distance of the endpoints. Okay, this is equivalent in the vector space setting. It's an approximation to manifold setting, but this can easily be done and seems somehow natural. We will later on see that this can again be interpreted as such a distance function, but for the moment we can just replace this by the distance of the endpoints. Okay, and this is very nice because this gives us a very simple expression which can also be easily computed numerically, and this, for instance, convex in Hadamard spaces. Now we are left with the second term here, which we still need to measure the distance of 2 point tuples, where we have the problem that these 2 point tuples now, they live on different tangential spaces. Okay, so the first point always identifies the tangential space, and the problem is that the 2 point tuples live on different spaces. So the question is, what is an appropriate distance function for this kind of point tuples? And before we dive into that, we will come back to the main properties of TGV. So we ask ourselves the question of what is a good choice for this distance function, and to get an intuition of what might make sense, we would like to repeat these properties of TGV we have seen before in the vector space setting, and for that we need some kind of generalization of the involved concepts, in particular of affine functions. So what's an affine function on a manifold? And in the univariate setting this is quite straightforward. So on a manifold, geodesics somehow correspond to straight lines, which means that a signal is affine if and only if it's geodesic, so we call it geodesic if and only if all the points are on the same geodesic at equal distance. Okay, so this is I think a really like the generic generalization of affine. So you have some values here, and you say u minus, u naught, and u plus, and you say the function is affine if you can draw a geodesic such that all the points are on the same geodesic and the distance is the same. This exactly corresponds to affine in the vector space setting. And so having this, we have everything ready that we need to state our required properties for a manifold TGV. First of all, we say, well, the obvious thing to say is that in the vector space setting it needs to reduce to TGV because we want to generalize it. Then we can say, okay, if the minimum is attained at y equals u, which means that these point tuples correspond to 0 vectors. So remember, if y equals u, we have here a point tuple uu, which is equivalent to a 0 vector. So if we take 0 here, we obtain TV, where TV is this obvious generalization of TV to the manifold setting. On the other hand, if we take y to be the endpoints, which means that this corresponds to the forward difference stencil of u, which means that this vanishes, we require that the function reduces to second order TV, where second order TV needs to be an admissible generalization of second order TV in the sense that it reduces to second order TV in the vector space setting. So we get an appropriate version of second order TV for manifolds. And the last requirement, and this is the most crucial and difficult one, the most restrictive one, is that we require the manifold TGV is 0 if and only if the signal is locally geodesic, meaning that for every 3 point section it is affine, so to say. Okay, and this is equivalent to affine in the vector space setting. However, there is a subtle difference due to non-uniqueness of geodesics. So if you have non-unique geodesics, it might be that local and globally geodesic differs, but for the sake of the talk you can assume it's the same. So if the signals are close enough, it's the same notion. It's just a small technical difference. But those are not the 4 properties that you would like to maintain with our generalization. And now we can say, okay, how does this transfer to requirements in a distance function? And this is quite straightforward. So we have just some basic requirements for MP1 to MP3. Namely, we say that the distance of 2 0 tuples must be 0, independent of the location. Okay, so if I have 2 tuples where starting point and end point is the same, which means that they correspond to 0 vectors in the tangent plane of x and u, then the distance must also be 0. So in this case, it doesn't matter how distant the points x and u are, but it just needs to be 0. This is essentially it's the only real property, because the other one just states that in the vector space case this reduces to what we have, namely that you take the difference of endpoint and starting point and subtract them. So this is just a compatibility condition with the vector space case. And one can show that if these 2 properties hold, then this properties MP1 to MP3 hold. So we generalize TGV, we get TV and we get TV2. The more difficult part is MP4. And for this we have the further requirement that we say if we have a signal now, if we plug in two tuples where the endpoint of the one is the starting point of the other. So if we are in this situation, so we have ui minus 1, ui, and ui plus 1. So we have, on the one hand, we have this tuple here, and on the other hand we have this tuple, and they are connected, so they are not arbitrary, then we say if the distance of these tuples is 0, then the tuple must be geodesic and the other way around. Okay, so if there is a geodesic which connects the 3 at equal distance, then the distance must be 0, and if the distance is 0, the tuple must be geodesic. Okay, so these are somehow things that we can now keep in mind when we construct a distance function. And now the question is how to do this. And as I said, there are several ways. We have 2 ways, but I'm just going to talk about 1 way here. So consider now the situation. So we have one point W and V, and the other one would be X and Y, and we want to measure the distance somehow. And for instance, we cannot just take the product distance because this would not satisfy our properties. The intuition is somehow those correspond to tangent vectors in a different location, and we would like to somehow transport them to the same location and then take the distance there. Okay. So the issue is just that they don't live in the same location. If they would live in the same location, or if you would be in the vector space setting where all tangential spaces coincide, you wouldn't have a problem. So we just need to somehow transport them. And there is a well-known concept of transport, which is called parallel transport in manifolds, which is defined for tangential vectors. So we can look at the tangential vector here, the log of u, v, and then there would be a notion of parallel transport, which allows us to transport this tangential vector to this location. And then we could just take, again, the log here and take the difference. This would be one possibility. But in order to not involve, again, now tangential vectors, we would like to keep it more simple, and we take an approximation of this. We do the following. So we first take the center point of x and v, and then we mirror the point u at the center point to obtain a point y prime. And it's like an old fact in manifolds that, like for infinitesimally small distances, this vector now, the log of y prime at x, approximates the parallel transport here. Okay, so this is a lower order approximation of the parallel transport. You can interpret it this way, but you can also just ignore this fact and take it as a distance function of point tuples. So what we do is we say, okay, we have just 2 basic operations, taking the center point and mirroring, which gives us a point y prime. And then we interpret the point tuple x and y prime to be the transported point tuple, and now it lives in the same location as x and y, so we can take the distance. And this is exactly what we do. So and now, since again in the case of non-unique geodesics we have to minimize over all this, but basically we take C, which is now the center point between x and v, then we take y prime, which is the mirror, so this means take the geodesic between u and C and go like a double length. So we mirror it to get y prime, and then we just measure the distance of y prime and y. Okay, and this would be a distance type function. We call it distance type function because it's not really a distance function, but this would be a candidate for a distance function of point tuples. And you might think of many other things to do this. For instance, this is non-symmetric. You can try to think of symmetric variants, but in order to have this nice interpretation of parallel transport, we decided to use this version. And what we actually could, so this now allows us to define TGV for manifolds in the univariate setting. So we just replace this generic distance function by this concrete distance function, which is simple in the sense that we only need points in the manifold. We only need to mirror and take averages, which is also needed, at least taking averages would be needed for second order TV also. So essentially it's not much more difficult. And what one can show is that using this definition of MTGV, which is now STGV because of the Shields distance, we can show that this function satisfies the properties MP1 to MP4. So it's really somehow a reasonable generalization of TGV in the sense that it is a generalization. You can get TV, you can get second order TV, and most importantly, you also know what the kernel is. You know that this function is 0 if and only if the univariate signal is geodesic, or locally geodesic. Okay, so this would be the univariate setting. And that, as I said, so the main idea is now take point tuples, transport them, and take the distance. And the concrete instance is just the way how we transport. You can think of other ways to transport, okay? But now we come to the bivariate setting, and this is where it gets a bit more complicated, because we have this essentially because of the symmetrized gradient. But again, we will see that somehow the properties that we require from our generalization will guide us towards what is an appropriate choice or what is an appropriate generalization. So let's start again with the vector space setting. So I'm writing down now second order TGV in the bivariate setting. We have now a gradient, a discrete gradient, and a discrete symmetric gradient. What's important to notice here, I take anisotropic norms. So this is what's usually done on manifolds, because then you separate some of the different distance functions and you can get explicit proximal mappings. But this is of course something which one would like to improve upon. But for the moment we stick to the, as it's done with TV and second order TV, we stick with anisotropic norms. So we just write this now in more detail. The first part corresponds to the x derivative, and we subtract the vector field W1. The second part corresponds to the y derivative, and we subtract the vector field W2. So this is just writing out the blue term here. And then we write out the green term. So again, remember the symmetric gradient. First we take an x derivative of W1, y derivative of W2, and then we have this averaging. We take the y derivative of W1 and the x derivative of W2. And now we go on. We try, we see how can we generalize this with what we have already obtained in the univariate setting, and most of the things are quite straightforward. So first we make this identification again with point tuples. So here we have now the x derivative corresponds to a point tuple where we have I plus 1 here, the y derivative with j plus 1, and for this W1 and 2 you introduce two endpoints, y1 and y2, so you have also again this identification, and then you see that this is again just the difference of point tuples, so we can plug in our distance function that we already have. So for this we do not need anything more. And in this particular case, we are again in the situation that the starting points are all the same. So the distance function reduces, and in fact we can even show this for the Shields distance in case of univariate geodesics, that these two things coincide. So you can also plug in the Shields distance and you get the same, this simplified distance here. So this is very simple. We just have two distance functions on a manifold, to ui plus 1, j plus 1, and the endpoint. Now what's about the first part of the symmetric gradient? Well, we can again replace vectors by point tuples. We see that we again have just differences of point tuples. So again, we can just plug in our distance function. Now in this case, we do not live in the same location, so we have to use the Shield distance, but still this can all be captured with things that we already have. But now if we look at the third part, we see we can again replace everything by point tuples, but what we see now is that we have the distance of point tuples twice, and then we add 2 point tuples. And I think I forgot the 1/2 here. Or written in another way, we would need to add point tuples and take the distance. So this is something which is not captured by our framework. We need some kind of algebraic operations on these point tuples. Okay, so the difficult thing is, the only difficulty in going to the bivariate setting is really how to extend the symmetric gradient defined for these point tuples to the bivariate setting. And again, as with the univariate setting, we will first assume we have it. So assume that we have now a symmetry as dsym, so a distance for the symmetric gradient, and let's see what properties would need to be fulfilled by this dsym in order to get to transfer our properties. So the question is, what is a good choice of dsym? So first we need to again say what is a generalization of affine. So there is not a unique way now in the bivariate setting, but I think there's a direct way. So we say that the bivariate signal is locally geodesic, which means that generalized affine if and only if it's geodesic in the horizontal direction, in the vertical direction, and in one diagonal direction. Okay, so if you maybe draw this. So now we have a bivariate signal. I just consider a section of the signal, so 3 by 3 section, and we say the signal is affine if it's affine in this direction. So geodesic in this direction, and in addition, in order to capture mixed derivatives, we also require that it's geodesic in the diagonal direction. Okay, in the vector space setting, you immediately get then that it's also geodesic in this direction. This is what you do not get in manifolds in general. So one way would be to also require this, but in order to be less restrictive, because we think this might even be a too hard requirement, we just require one direction. But but you need at least one diagonal direction in order to capture mixed derivatives. Okay, so we say a signal is bivariate signal is geodesic, so generalized affine if and only if horizontally, vertically, and diagonally it's geodesic. And then we can again formulate the properties that we would require of a reasonable generalization of TGV to the manifold setting. So first, we say it needs to be a generalization, so it needs to reduce to TGV in vector spaces, where now, as I said, we use the anisotropic norm. Second, we say that if the minimum is attained at U, so if this point tuples here correspond to 0 vectors, then we want to obtain TV. If the minimum is obtained at U I plus 1, meaning that these point tuples here correspond to finite differences, then we get second order TV, where again second order TV is an admissible generalization of second order TV. And the last and most crucial property that we require is again, it's 0 if and only if the signal is locally geodesic. And you will see that this is somehow the property that restricts us very much in how to extend the bivariate setting, how to define the symmetrous distance. Okay, so we keep in mind that we want to define the symmetric distance here in a way that these four properties are fulfilled. And this translates again to properties on the symmetric distance, namely similar as before. So if we plug in 0 vectors, the distance needs to be 0 independent of the location. It needs to reduce to the right thing in vector spaces, obviously, because we want to generalize vector spaces. Then we again get that NP1 and 2 NP3 holds. And in addition, we have this property, and please don't read it, I will try to draw it. So this is basically again a local property on 3 by 3 signals, and it states the following. So if the signal is geodesic horizontally and vertically, okay, if we already have this, and the symmetric distance is 0, then it must be also geodesic in the diagonal direction, so, which is the obvious thing to ask. So we really need the symmetrous gradient in order to get this diagonal derivatives, and also the other way around. So if you are geodesic in all directions, then the function must be 0. Okay, so we have now we know what we need to require of our I call it symmetric distance, but it's not symmetric. So now let's look how we can achieve this. So again, a plot. So this is what it would need to look like in the vector space setting. So we can plug in the point tuple representation of the vectors. And as I said before, the problem here is that we need some kind of algebraic operations on point tuples. So we see that we have somehow a combination of differences and sums of point tuples. So we can look if there's any way to do this. So for instance, if you take the sum of 2 point tuples and we just plug in what we have in the vector space setting, we see that this corresponds to this situation. So say we have one vector here, and we have another vector here. So it's somehow not clear what is the appropriate point tuple that corresponds to the sum. However, if you take the difference of 2 point tuples, which live at the same location, so for the moment I just ignore that we have different tangent spaces. If you just plug in the definition of the difference of point tuples, we see that the base point factors out, and we get another point tuple. Okay? So this is something we can define. So if we have point tuples which live on the same location, we can somehow define the difference of 2 point tuples, and we will get again a point tuple. So this means if you can reformulate this using differences of point tuples, maybe we can gain something. And indeed, this can be easily done. So we just change the sign here, and now we see that we have once the difference of point tuples and another time the difference of point tuples. So this, if you ignore the tangent spaces, can be again regarded as a point tuple, and then we would just have once the distance of 2 point tuples, which we can capture by our previous distance function. This would be fine. However, one can also realize that this is not the only way to do it. So there's another way. So you can also rewrite it like this, and you have again just the differences of point tuples. So the question is there a generic way, which one is the right way? And to find this out, we have to look a bit more closer on our requirements. And we have, so we look now at the situation that I have also drawn on the blackboard. So when we look again at the difference of the point tuples, we can see that the order in which we take the differences, and now we regard the more general situation that tangential spaces do not coincide, the order in which we take the difference of point tuples defines how we need to transport. So if you first take the difference of these 2 point tuples, it means that we have to transport this vector up, and if we then take the difference of these 2 point tuples, it means that we have to transport this vector here. Then we can take the differences and we are done. The other choice, which is which is the same in the vector space setting, would correspond to transporting this vector here, and then transporting this vector down, and again take the difference. And the question is, what is the right choice? And this is exactly where these requirements will help us. Namely, we consider now the situation that MTGV is 0. Okay? And we want, in this situation, we want to be able to conclude that our signal is then locally geodesic. So if MTGV is 0 from the other terms, we already get that the signal is horizontally and vertically geodesic. Okay? So we need our symmetrized distance to conclude that it's geodesic in the diagonal way and the diagonal direction, which means that we need somehow to transport these vectors in a way such that we know what happens. And now there is a problem, namely if we transport W1 up due to holonomy, so since we are in a manifold, we know that W1 now points exactly to this knot here. But if you transport it, we can not say that the transported vector will again point here. We lose this information. It might be that the manifold has some geometric structure here in between, which somehow rotates the vector, so we cannot know this. So this somehow tells us that this just transporting up is not feasible, because we cannot have any information on the transported vector. However, there's one fact, namely, in this situation, we see already that the W's are tangential vectors of the geodesic. So they coincide, they're parallel to the derivative of the geodesic. And if we transport the vectors which are tangential to the geodesic along the geodesic itself, we know that we will again get a vector which is tangential. Or in another way, if we transport this vector down, and we know that the original vector has pointed here, then the transported vector will point here. So we have some information. And this is why what restricts us essentially, that we can only transport the W2, we can only transport them vertically, and the W1, we can only transport them horizontally. And this is the restriction which excludes one of the cases. Okay. So this is feasible, because if you transport, we still know what happens. And so this is exactly what we will do now. We take the second definition here. So first we transport this vector down, even though this is not obvious, because the obvious thing would be to transport everything to the same location, and then it's easier. But if we do this, we do not know, due to holonomy, what happens. So what we need to do is we need to transport this vector down. We can transport this vector to the left. Then we have two vectors which live in the same tangential space. We can take our difference operation, which gives us now the vectors d1 and d2. And then we have again two vectors of which we need to take the difference, and this we can use with our distance type function, which we already have. So explicitly it looks complicated, but it's very simple. So this corresponds to just one transport using the Schild distance. This is another transport, which gives us now these two vectors. And then we again use just the distance that we already have to take the distance of these two vectors. And by construction, we can show that using this symmetrized distance, as motivated before, the generalization indeed satisfies the properties MP1 to MP3, and for the talk I assume unique geodesics also MP4. Okay, so the point is really that this property MP4 restricts us to certain transport directions and somehow uniquely tells us how we can generalize this setting. Okay, so since time is limited, I will skip this. So we can show that all these distances are lower semi-continuous, and we get existence for denoising, and also that TGV is lower semi-continuous, and so on. Just some words about the algorithmic approach, and this is something where we might certainly improvement might be beneficial. So in the univariate setting, we need to solve now the following problem. So we have a data term for the denoising. We have one term which corresponds to the TV term, which is very simple. It's just the distance on a manifold. But this is, I think, one of the main points, that one term is very simple. And then we have this abstract distance function. And this is not more difficult than TV2. So overall, I think it's not more difficult to solve numerically than second order TV. You just need the same operations. And one approach to do this, and that what we employed actually, is cyclic proximal point. So this is an algorithm which works in manifolds and which is designed for the situation that you want to minimize the sum of several functions, and you just iterate the proximal mappings of all these functions. So you iterate once through all the functions, the proximal mappings, then you update your steps as parameter and you iterate again. So you just, and all these things can be done in the manifold setting. There's some convergence theory about that. So if the step sizes are not summable but squared summable, which means that they must go to 0, this is a disadvantage. And if the manifold is Hadamard and all terms are convex, then one knows that this converges actually to a minimizer. In our setting, if we look at H1, the prox is explicit and it's convex. If you look at H2, the prox is explicit and convex. However, GI is non-explicit and most likely non-convex. So this is a disadvantage, which is also the case, for instance, for second-order TV, and I think which is not easy to get rid of. So we can use the cyclic proximal point. However, due to this third term, we lose convexity, and we also lose this nice thing that we have an explicit prox, and we need to numerically approximate this, which is possible in symmetric spaces, and which requires about 10 pages of computation to get the derivatives right and so on, which I skip here for detail, for the sake of time. And at the end, I just want to go quickly through the numerical experiments. So we have two parameters here in TGV. We parameterize this in the way that we have one parameter S, which corresponds to balancing between TV and TV2. So if we go to 0, we have TV, and if we go to 1, we have TV2, and R, which corresponds to regularization, and we measure the improvement in delta S and R. Just remember, higher delta S and R is better. So what we did several experiments. One thing what we did, and I think this is interesting, is a consistency test. So we considered the S1, and we considered data which is only on the positive, as on the half of the circle. So we can unroll the data and compare to the vector space situation. So we have, on the one hand, we have our code, which works for S1 data, and on the other hand, we have a one-to-one correspondence to vector space situation, where we can compute a numerical ground truth using the John-Paul-Pock algorithm. And I really took care that this is, we really have a good approximation of the ground truth, and we did this for different parameters. Now you see S0.5 should correspond to TV more or less, subject to a linear term. S0.95 should correspond to second order TV, and S0.3 should correspond to something in between, namely TGV. And you see, at least in this plot, you don't see a lot of much difference. If you look closer, you see some difference, but what you can also observe is the model somehow does the right thing. Namely, the blue line, which corresponds to TV, jumps. So this is what you would expect from TV. You have some linear ascent, but this is due to the model, because if you drive the parameters in TGV to infinity, you get TV subject to a linear term, which is for free. So this is really what you would expect from the continuous setting. You cannot expect TV. If you use S0.95, you see that you have no jumps. So you have a piecewise linear approximation. And if you use something in between, you can see here that you have jumps. In some other locations you see it better. So you get really somehow the effect of TGV. And again, it's similar. So this is the vector space setting, manifold. It's similar but not identical. We also made this test for S2. So we have here unnoisy ground truth. Here we have TV, second order TV, and TGV, choosing these parameters. And we see that driving the parameter towards TV, we can get jump discontinuities. Driving it towards second order TV, we see we have no jumps. And in between, we have jumps and also linear parts. And this can also be maintained with some noise, so you have a similar effect. And even with quite strong noise, you see that you can still get, in particular for this choice, which really corresponds to TGV, you can get a reasonable reconstruction. And at last, so we have, so we also tested bivariate data, so this would be S2 data, where we compared to TV, second order TV, and our method, choosing optimal parameters. Obviously better than TV, these two, and if you compare closely, you see that we have really jumps, which do not appear that well in second order TV, so, which is what you would expect. And we also have real data applications with HeightNet imaging and DTI, which I will just quickly jump over. So just to summarize, so what we have seen in this talk was we systematically, I think, generalized TGV for manifolds. We have somehow an axiomatic framework, what reasonable generalizations would be, and we have proposed concrete instances. We have ensured basic properties, such as existence, for instance, and we have at least shown that it's numerically feasible, even though the algorithmic part certainly needs to be improved, and this is also something which for the future directions. And then another thing would, of course, be to see how this can be done in the infinite dimensional setting also. So thank you for your attention. I just plot some references here, so those are most of the references. If you want to find our paper is on arXiv, so you can get it here. And I recently heard that there is also a paper which has been uploaded 3 days ago on arXiv by Gabi, who also just tested TGV for manifold-valued data. So we have now 2 papers on this topic, and you can look at both and see. Okay, so thank you a lot for your attention.
So in the interest of time, I think we move to questions. I'm sure there are many, to the coffee break, and we meet again at 4:10. Thank you.